My suggestion to you is don't copy the answers yet. Okay? Don't copy it. I very much prefer for you to try it yourself. You want the answers after, you look for me after. Okay? But this one is like math. Don't lose the opportunity to practice it. Okay, you can practice it, practice it. Okay, once you see the answers, it's like as good as you lose the opportunity to do this question. Okay? Yeah? So let's go through the MCQs first. Okay, MCQs goes with B, D, A, B. B, D, A, B. Okay, next. C, B, D, A. C, B, D, A.
I got one wrong.
That's all.
My senior just ran 5-1.
Okay. Is there any particular question you'd like me to go through? The last one. Okay. Anything else? Are the rest doable? Question, yes? Question A. Is that the last question?
Yes.
Anything else? No? Okay, that's the question A. Question A.
Mr. Tan's hair is poking out from the back of his head. It will become a very popular comedy show.
Yeah, question A, do you mind if I go through the next lesson? Yeah, I'll check with the other teachers on whether this is something we are going to test you properly on. Okay, so I remember Henry also asked this question. I didn't look through carefully, but now that I'm looking through, I'll get back to you on how, to what depth you need to know how to do this question. Okay, syllabus has changed over the years. I'll get back to you by tomorrow. Okay, tomorrow we'll go through this question in depth if it's something that we want you to understand. Okay? Okay, so we move on to structure questions. Why looks so weird on my... I hope your printer one doesn't look so weird. Yours looks okay? Okay, mine looks a bit weird lah. What is this? 53 on top, 127 below. Oh, 127 on top, 53 below. 138 on top. Okay, if you've not attempted, you could attempt while you're going through.
Why do you have so much more?
Yeah, whatever we're doing here is nothing quite new. We're just trying to see if you understand what's the meaning of nuclear number, atomic number, protons, electrons, neutrons. Okay? Skills that we've been practicing many times in class. But is there anything that you found tricky about this question that you'd like me to go through? Okay, if not, I'll move on to the next part. Okay, the way mine is formatted looks a bit weird. You format it in the correct format with the atomic number and the proton number and the nuclear number in the correct place. Hey. Which other RE? So you completed everything? So can I, since you never bring, I need to know if you've done it. So can you submit tomorrow? Yeah, I'm going to collect from you at least.
There's two 27 for C and D.
For C and D?
Yeah, it said you can only use
Oh, okay.
small ones.
I see.
You can use it once, more than once, or more.
What did the question say?
Oh, you can.
You can use each symbol once,
You can use it
more than once, or not at all.
Not wrong.
Okay? Okay, you can use each symbol once, more than once, or not at all. Yes?
You just write the letter.
Oh, okay. So can you just write the letter? Okay, that's a great question. If we provided you the entire symbol with the nuclear number plus the atomic number, will you write the entire thing? But good point. Sometimes we may just provide the letter. We just provide the letter, then go ahead and just write the letter. What if we provide you this piece of information and actually you can find out the exact identity of the element from the periodic table? Technically you can, right? You look at the periodic table, you then go and find out exactly which element this is. Because all of this is not based off fake elements. So technically you can find out, right? Okay. So let's say you know the identity of Q. And you think identity of Q is, actually what is Q? 13. Isotope, hydrogen. Okay. Maybe R. Okay, what's R? R is 7. R is 3. So R will be lithium. Let's say you know R is lithium. Okay, you know it's lithium, based off the periodic table. Can you write lithium in your answer? No, don't write lithium in your answer. Because it's not what we provided you. So always use the alphabets that we provide you in the question itself. Even if you, after looking at the periodic table, you know exactly what element this is. Okay? Answer the question. Don't use the information from periodic table unless we ask you to. Okay? Yes? Oh, but she brought her worksheet. Oh, okay, sure. You want to? Yeah. Yes? Ishan? Okay, hold on up. 2814p. 28. Oh, okay. 2814t, is it? Okay, so what did they ask for? Which atom represents a period 3 metallic element? 2814t. Okay, so if it's something is in period 3, that means we are looking for how many electron shells it likely has. Okay, we look at 14. I'm just doing the question as I go. So 2, 8, 4. It seems okay, right? Okay, so 14. Then we look inside the, we look at the periodic table. If this is 14, 14 is silicon. Right, if you want to be specific about it, 14 is silicon. Silicon is not quite metal, not quite a non-metal. is along a staircase, we will consider that more specifically a metalloid. Okay, so this is more of a metalloid. We will consider those metals as metals if we find it more to the extreme left. Right? If you find it to the left hand side, as long as it's not directly near the staircase, we will consider it a metal if it's on the left hand side of the periodic table. Okay? So that's perhaps why it's not counted. Yes, Henry? Oh, just raising your yawning. Okay, next, define the term isotope. 3b. Okay, 3b is one of the tougher questions you can encounter in the topic of atomic structure. Maybe you want to star it so that you can practice it again next time. Okay, this question, you should know how to do it at the end of the day. Relative atomic mass. How to calculate relative atomic mass? I've gone through an example in class of how to calculate atomic mass, relative atomic mass before. Yeah. Okay, so this particular question, you need to know how to do it. Okay, so how will you calculate relative atomic mass? Relative atomic mass is like finding the average mass of all the different isotopes present, but proportionate. It's a proportionate kind of average. So for example, if we look at, let's look at the isotope of 234U. That is the mass number of that particular isotope. 235U, that is the mass number of that particular isotope. It's just one unit heavier. And then there's 236, 238. Relative abundance shows what's the proportion of this particular isotope on Earth. So we just scan across the board. Which isotope has the highest abundance on Earth? 234, 235, 236, 238. Okay, it's 235 that has the highest abundance on Earth. Right, so that one has the highest abundance. That's how we interpret this data. So how do we calculate the average in that sense? What we will do is we will take the percentage and then we'll multiply by the mass. So in this case, you observe that, for example, the first one, they take 13.7, divide by 100. We want to find the percentage times 234. Okay, then they go and add and they do the same thing for the rest. 62.2 divided by 100 times that particular mass, 235, and so on and so forth. Then you should get the answer for it. I would like to share with you another way this question could be phrased, or the information provided to you. Sometimes the relative abundance, they won't give you 13.7. Sometimes they will give you already the pre-divide for you, the 100. Okay, so for example, sometimes the piece of information they provide may be this. If you want to, you can draw another table below. You can draw a third row below all of them all. You draw a third row and then there's 1, 2, 3. Okay? In this third row, sometimes you may see it provided to you in this way. They already pre-divide everything for you. 13.7 divided by 100. This will be what? 0.137. Okay, sometimes they provide the information to you already pre-divided. So 0.137. You go and do the same for the rest. 0.622, 0.155, 0.8608, wrong. 0.086. If everything has been pre-divided for you, actually you don't need to do that step of dividing by 100. All you have to do is 0.137 times 234 plus 0.622 times 235 and so on and so forth. Okay, if they provide you information in this way. How do you know that you don't need to divide by 100? Well, you can check one way. One way to check is that if you add everything together, it equals to 1. If it equals to 1, you don't need to do any division by 100. Okay? If you go and add all the values, in that case, it will add up to 100. If you add all of them up, it equals to 100. you need to divide by 100 plus. Okay? Yeah, so take note, there are two ways relative abundance may be provided to you in the question. This question difficult, or is it something you've done in math before? I don't know. Math, you all got to do this kind of average before. Primary school you've done it before. So this is a primary school level question. In the math part. Okay, we go to question 4. Okay, question 4 actually, you may have found difficulty doing this question before we went into the lesson on ions. Okay, but after we got into the lesson of ions, you will find that the part of the question that you may have trouble doing is this particular one over here. Okay, they ask for the number of electrons for calcium ion. That question, that part, you may have difficulty doing if we have not gone through the topic of ions yet. Okay, so ions, Ca2 plus. We know that the atomic number is 20, so it has 2, 8, 8. My math very bad. This is 10, 18, 2. Okay, so if there's, oh hello, okay, so that's your senior Nash. Okay, so 2, 8, 8, 2. So she's here to catch me if I score you all. Okay, so 2, 8, 8, 2. What's going to happen is that if you see there's a Ca2 plus, okay, that means to say it's no longer calcium. It's no longer calcium. This long calcium, this is the electronic configuration of calcium. Ca2 plus will mean that it has lost 2 of its electrons. So that means now it's 2, 8, 8. So there are 18 electrons, and that's the last box over there. Everything else is quite the standard, but it's just the last box that we have threw you off. If you didn't think back to the topic on ions. Okay, but after we step on the chapter on ions, maybe this question will be better for you. Okay, before I move to the last part, I'd like you to have a look at the way each other drew your electronic configuration. Okay, what do your circles look like? Do they look like circles? Are they squares? Are they ovals? At this point, you are also quite good at checking each other's answers already. Have a look at each other's drawings. Okay, give us a quick swap. How do you draw each other? How do you draw the drawing? Okay, I think for our class we practice it so many times. Okay, hopefully by now when you look at each other's answers, you can also spot areas you can work on. Ready, Okay, so you will ask to draw the electronic configuration for carbon and oxygen. The number of neutrons is not what you expect. Right? You have to follow whatever has been provided to you, the neutron number. So just a quick one. This is carbon. What is the number of neutrons for this particular isotope of carbon? Okay, many of you have done it already, right? So what's the number of neutrons for this particular isotope of carbon? It's 13. It's not the usual 12 that we will normally see. So you see 13, right? So how many is it? Wait. Neutrons. Okay, what's the number of neutrons for this isotope of carbon? 7. Agreeable? 7. Okay, let's try for this one. Oxygen. The atomic number for oxygen is 8. Here they put 18 as the neutron number. So what is the number of neutrons that oxygen has? Isabel? 10. Okay. Everyone agreeable? Okay, so 10 is the neutron number. 10 is the number of neutrons. 8 would be the number of protons, or the atomic number. Okay, so let's have a look. 2, 4, 2, 6. I would say this is the suggested answer. But has anyone drawn it in a slightly different way? just to double check. Okay, did anyone draw it in a slightly different way? 1, 2, 3, 4, 5, 6. Yes, how young?
I put the fair one at the top, one at the left.
Oh, okay. So how young are you saying that? Sorry, let me erase the whiteboard. How young are you saying that yours is drawn like that? Your outermost ring, you put. Okay, let me draw all four first. So where do you put your tabs?
One at the top, one at the left.
Say one at the top, one at the left. Like that, is it?
Yeah.
Okay, that one okay. Okay. Although ideally, if you can spread out the pairs as much as possible, that's what I will normally do. But you will not be faulted for this if you do this. Okay, any other variations you have? Okay, so the inside circles, you put your crosses up, down. And, okay. Anyone use dot instead of cross? Okay. There's nothing wrong with dot per se. It's just that sometimes your dots are a bit too small. Then I cannot see the electrons. So that's why we prefer crosses just so that we know that you're doing good work. Okay, so if you put a dot, honestly sometimes you cannot see. Right? So if you put a cross, it's easier for us to see. Then we know that you've done it right. Okay? So this is the practice for atomic structure. The next RE that is in line is 5.1. We've already done that for ionic compounds. We did it in class. Okay? So we'll do the same thing. Once I'm done with the covalent compounds, we will do it in class immediately. And you have less RE. Okay? This particular chapter, there are quite a lot of REs, but we want to practice. Practice makes perfect. But we also need to know if we practice the wrong thing also, it gets worse and worse. But that's why we check with each other. Yeah. One thing I like about our class at the moment is that you all can check each other quite well. Okay, so to you keep this RE. Take out your textbook. We will complete the chapter on ionic compounds. Okay, so far what we've done for ionic compounds is that number one, you know how to draw the ions. Right? You look at the element, then you can tell roughly, do I have to give away electrons or do I have to gain electrons? What is your benchmark for whether you have to give away electrons or to gain electrons? In your own words, what is your standard? Ready? Okay, so what do you use as a gauge for whether you have to give up electrons or you have to gain electrons? Okay, what's your gauge? Hannah? Ready? Henry?
Plus minus 3.
Huh? What? Plus minus 3?
Yeah. Like you can, if you have less than 4 electrons,
Okay.
lose 3.
If you have less than 4 electrons,
you lose
you will lose 3 electrons. Oh, okay. I sort of get what you're saying. Okay, so for example, are you saying 2, 8? Give me an example. 2, 8, 3.
Yeah.
So you're saying if it's less than 4,
Yeah.
you would lose the electrons.
Yeah.
Okay. Why would you rather lose these 3 electrons than to gain 5 more?
Like less energy in that.
Okay, that's one way of interpreting it. Right? In JH3, we will give you more specific terms, but the way we can interpret it now is that it's just less effort. Less effort to lose 3 to gain the noble gas configuration. So the word is noble gas configuration. Just less effort, right, to lose the 3. But the idea is that we want to gain this noble gas configuration. As opposed to, let's say I have, so just now I was saying more than 4. Okay, so it is a 5. We will rather, in this case, gain electrons. Easier to gain 3 than to lose so many more, right, to gain this noble gas configuration. And that's how you decide what kind of an ion you will form. Okay, another quick recap. You can discuss with your friends if you want to. Metals. Metals tend to form what kind of ions? And non-metals tend to form what kind of ions? Yes?
What if like the atom only got 1 electron?
Oh, an example? Actually, there's an element with an example. So how you ask what if the atom has 1 electron?
Hydrogen.
Hydrogen, right? Hydrogen has 1 electron. It's a great question. Do we lose electron or do we gain electron?
Gain.
Why would you want to gain?
Because if not, you don't have even you have 0 electron.
Okay, so that's one way you can look at it also. In hydrogen's case, from what I've observed, it tends to gain electrons to form in the end H. Okay, what did I say? No. Actually, so from what I observed, I'm going all wrong, H plus. I tend to find hydrogen as an H plus. So that means it will have lost an electron. Okay, such as no electrons. But I've also seen cases where there are H minus. I've also seen that before. So in this case, it's quite a unique case, whether you lose or gain electrons. Hello, it depends on the situation. However, I've seen this a lot more. Okay, I see this a lot more. Hydrogen tends to lose electrons a lot more. Okay, so that's an interesting question. So my question is, for metals and non-metals, what kind of an ion do they form? Positive, negative, which one is which? Okay, Josh? You pick and choose which one you want to say. Okay, Josh says metals tend to form positive ions. And therefore, when we look at non-metals, they tend to form negative ions. Thank you. And it is because they are oppositely charged and what brings them together. Opposites attract. Okay, so a quick recap of the simulation we've been watching last week. If we have 2 of the same kind of ions coming together, there is a sort of repulsive force. Right? Unless, you know what, how I say, you go and corner this fella, then you know where to go. Right? Okay, but after I corner this fella and I let go, there's still this repulsive force. However, let's have a look at, we have oppositely charged ions. If I bring them close enough, there's an attractive force. Okay, this is the attractive force that we're referring to, and that is the ionic bonding that we're talking about. Opposite charges attract and stick to each other, whereas alike charges will repel. Okay, and an ionic bond makes use of that. What Josh was sharing just now, metals tend to form positive ions, and you will find them to the left side of the staircase. Non-metals tend to form negative ions. You find it on the right-hand side of the staircase. Okay, this is what Josh recapped for us. Okay, so let's just look at sodium and chlorine for now. Look at sodium and chlorine now. Let's watch what happens. We have sodium and chlorine. Sodium being the metal will lose electrons, chlorine being the non-metal will gain electrons. Okay, there's a losing and a gaining of electrons. In losing and gaining electrons, they become oppositely charged. And because they are oppositely charged, they start to attract each other. That's what an ionic bond is. However, now we're going to move on to the next stage. So far, actually the assumption we've been making is that one sodium will attract another chlorine. But is that really the case? In the real world, that's not what happens. In the real world, this is what happens. Let's say we have a few sodium, we have a few chlorine. Okay? We think that the sodium and chlorine forms discrete molecules. Sodium and chlorine, just separate from each other. Actually, that's not the case. what actually happens is this. This is actually what happens. All the sodium, all the chlorine, all of them oppositely charged to each other, they all come together as one big mass. Okay? If I have more of them, this is what you see. You come together in one large assembly. This is the reality of what we see. Okay, so which part of the textbook am I now referring to? I'm specifically on page 74 of your textbook. Okay, if we take a textbook, look at page 74. Look at page 74, you would find something similar to what I'm showing on the screen, except this is in 2D. This is a 2D version. In your textbook on page 74, you see a 3D version. There are two ways they are showing you this. The first way on the left-hand side is a very compact version. The one on the right-hand side, what you will see is that they space it out so that they can show you the attraction between all the different ions. We call this structure a giant ionic lattice structure. Okay, we call this structure a giant ionic lattice structure. Perhaps you could highlight or underline this structure. Yes, the word giant is necessary. Okay, giant, ionic to represent the ionic bond. Lattice. The idea of a lattice means that it is quite continuous in a pattern. Structure. Last year math got lattice. And what did math define lattice as? Okay, in our case, when we talk about lattice, we're referring to like a continuous, repetitive, repeating pattern that is quite endless. So a giant ionic lattice structure. Another way to look at it, okay, that was 2D. Now let's look at it in 3D space. Now if I were to drag this around, you can see that this is more of the accurate model of what a giant ionic lattice structure looks like. So if you were to see an ionic compound that just says sodium, like that, sodium, and then no longer called chlorine, remember we now call it chloride. If you were to see this given to you, you need to understand that when we look at ionic compounds, actually they don't exist as just a molecule like that. They don't just float around like that. In reality, many of them come together in 3D space. You look at it in 3D, all of them come together attracted to each other in what we call a giant ionic lattice structure. That is the structure of ionic compound. So when you look at this, you need to be aware of that. Okay, so yes, Caleb. Okay, so Caleb asked, just now we look at the 2D structure. Where's the 2D structure? Okay, we look at the 2D structure. Would we consider the 2D structure a giant ionic lattice compound structure? Okay, so which one? This one over here, is it? Okay, would we consider this a giant ionic lattice structure? Maybe this one will be better. I would say it's just a different way of looking at things. This is a 2D representation. But if you look at this from another point of view, there will be more, and then it will be in 3D. Okay, so will we accept this as a giant ionic lattice structure? We would. If we were to ask you to draw it, this is the best you can draw. Unless you're very artistic, and then you go on to the 3D version, you'll be okay. Yes? Okay, so bear in mind it's 3D. However, if you were to be asked to draw it, 2D is okay. Yes? Oh yeah, okay. So Caleb is asking on this page, this square-like thing that they represented to you, is this a giant ionic lattice structure? Yeah, it is. It's another way of showing it. In this particular one, what they want to show you is all the lines they are showing is all the bonds. They want to show you where the attraction takes place. This is a more spread out version. Okay? But in reality, they should be very close to each other. The one you're showing on the left is the more spread out version. just to show you all the bonds. Okay? And which presents us a unique situation. Because if we look at a giant ionic lattice structure, actually there are so many chlorines, there are so many sodium. How? How do we write it out in an equation? Yeah, well, I need to spin this first and then let me go on to the next one. Will it slow down? No, it looks like it's going faster. Yeah, so let's look at this. Actually, we look at a giant ionic lattice structure, there are so many chlorine, so many sodium. If you were to look at this by right, we should write something like that. We will write something like Na3Cl3. Right? Because that's what we see. There is 1 chlorine, 2 chlorine, 3 chlorine. 1 sodium, 2 sodium, 3 sodium. So shouldn't the formula be Na3Cl3? But we don't. For ionic compounds, we simply write the smallest ratio of the ions relative to each other. Okay, the smallest ratio will do. So if we look at this, just an NaCl will do. That is the ratio. You see 3 sodiums, 3 chlorines, 1:1. Okay, that's what we will represent. Sodium chloride. Perhaps another example will make things a little bit clearer. We look at calcium and fluorine. Okay, so first and foremost, we do a quick practice. Which one of these formulas will be correct based on what you've done last week? Calcium and fluorine. What kind of an ion will calcium form? What kind of a charge will it have? What's the charge of fluorine? Then you tell me what is the formula of calcium fluoride. Okay, and now spend some time discussing with your friends if you want to. Number 1, what is the ion that calcium and fluorine will form? And therefore, what's the formula of its ionic compound? You can refer to your periodic table. In fact, I encourage you to. It's a great tool. So the question is, what is the charge of calcium? What's the charge of fluorine? Therefore, what's the compound we will form? Remember, calcium is a metal. So what kind of ion will it form? Fluorine is a non-metal. So what kind of ion will it form? Henry, question?
For the NaCl thing, right?
Yes.
Is there like a specific number?
Oh, or does it just go endlessly, is it?
Yeah, because I thought for every different one, it depends on like how many ions are near them.
Okay, so you're right. It will depend on how many chlorines and sodium were present during the reaction at this phase. If there's only so few, then we will get a sodium chloride that's only this large. But we have a lot of the sodium and chlorine provided, then we have a very, very large giant ionic lattice structure.
So it's not definite.
It's not definite. Or what is definite is the ratio. We will always find 1 sodium to 1 chlorine. But how large it gets depends on how much we provided in the first place. So, quick one. What's the charge of calcium? Christy. Think fast. What's the charge of calcium? Ion, sorry. +2? Okay, okay. I asked you what's the charge, right? So Christy is very specific, correct? The charge is +2. If I write it in formula form, it is 2 plus. Okay, calcium 2 plus. What is the charge of fluorine ion? Or now we call it fluoride. Emma? Fluorine, gain or lose electrons, what will be the charge of it? 3 minus. Do you have the periodic table with you? Okay. So where do you find fluorine? Fluorine is in 17. So how many valence electrons does fluorine have? In 17. 2, 8, 7. So would you want to gain or lose electrons? You want to gain. How many will you want to gain?
1.
1. So therefore fluorine will form a what kind of ion?
-1.
So Emma? Minus? You happy with that? Okay. Yeah, it's testing you. Okay, so fluorine minus. So these are the two ions we are working with. So what will be the formula for calcium fluoride? How many fluorines do we need for calcium?
2.
Jaden? 2? 2 calcium per fluorine? 2 fluorine per calcium. Make sense? Yeah? We need to kind of balance out the charges, right? So for every calcium we have 2 fluorines. So CaF2. Okay, CaF2. So CaF2. Right? So how many calciums, how many fluorines do we have? Ayo, let me count up. So there are 1, 2, 3, 4, 5, 6, 7, 8 fluorines. Okay, so in here you see 8 fluorines. How many calciums do you see? 4? Okay, does it fit the ratio? Yeah? So ionic compounds, when you see this, it is actually showing you the ratio of ions, positive and negative ions. They are showing you the ratio, not the exact number. Okay, you actually cannot find out the exact number, but you can know the ratio of it. Yes? Oh, okay. Without forming an ionic compound? Okay. Okay, Caleb is asking, can you form an ion without forming an ionic compound? Because it seems as though calcium needs to lose its electrons to somewhere before it can form an ion, right? So what we've learned so far is that you need to form an ionic compound first, right? Okay, wake up time. Okay, so great question. Can. You can actually find ions free roaming, especially when we are using it in water. Okay, so actually in water they are free to roam about. They remain, so it will remain in fluorine, but you're free to roam about. That's one property of ions. Of ionic compounds. Okay, we're now going to go into the properties of ionic compounds, which you can find on pages 74 to 75. These are the properties of an ionic compound. Okay, the first property of ionic compound is that it has extremely high melting and boiling point. Remember last year we learned about melting boiling points? Yes, got it. Okay, high melting and boiling points. So number one, ionic compounds have high melting boiling points because the ionic bond is extremely strong. Okay, so let's say I'm going to draw just a few ions together. Plus, minus, plus, minus, plus, minus, plus, minus. Okay. In between each one of these ions, the bond is extremely strong. To overcome them, you need a lot of energy. That's why you'll find that the boiling point is extremely high, melting point also extremely high. They very much prefer to be in their solid state. Okay, the bond is extremely strong. Yeah, so if you want to melt it or boil it, you have to supply heat energy. Did I teach you that heat energy? Right now? Heat energy.
Isn't it thermal energy?
I mean, they are kind of related, you know. Heat energy when. Oh. Shake it. Okay. Usually when you apply the kind of energy, only can reach the surface. Yeah. But when you apply heat energy, you can go to the core of the. Hey, no, you stay here for a while. Yeah. It's lesson ending soon already. Okay. Okay, so number one, there's very high melting and boiling points because the ionic bond is extremely strong. Number two, in your textbook it says they are good electrical conductors when molten or in aqueous solution. Okay, so you want to highlight the word aqueous solution. the word aqueous solution. What does aqueous solution mean? Okay, aqueous solution means this. Maybe we tackle the molten solution first. Molten state. They say they are good conductors of electricity when in molten. What does molten mean? Molten means melted. Okay, so I'm going to show you a melted form of an ionic compound within a box. What we learned last year is that when things are melted, they kind of roll past each other. So you look at all these ions now, they're not quite bound together in a very regular structure. They are free to roam about here and there. Okay, they're free to roll about. This is its molten state. What does aqueous mean? You see the word aqueous, it means that they are dissolved in water. So what would that look like? It will look like this. When it's dissolved in water, they're just free to roam about. You will have a plus over here, you have a minus over here, you have a plus over here, minus over here, a plus over here. They're just free to roam about. This is just water in between them all. Okay, this is what aqueous solution means. Yes?
Then what's in between the molten?
Oh, what's in between the molten? Nothing.
Air.
You could say it's air, but the space between is not very large. It's just that they are now moving like liquid state. Okay, molten means it is in liquid state. Yes, Yongchen?
Where did the water come from?
This one is it? Oh, okay. We have to provide it. So, for example, if I were to take sodium chloride, which is your table salt, you know, sometimes you add it in water. Yeah? When you add it in water, you are making it go into its aqueous state. And all the ions just separate out. Start to separate out the water.
Dissolve lah.
Yeah, dissolve. So when you dissolve something in water, the ionic compound, it becomes its aqueous state. But you know what's similar between aqueous state and molten state? Is that now the ions are mobile. Mobile means free to move. Okay, the ions now are free to move. Be it in aqueous state or molten state, free to move. And the beauty of that is, if they are free to move, they can conduct electricity. Okay? If they are free to move, they can conduct electricity. Yes, okay? So technically, if you melt salt, it can conduct electricity. If you dissolve salt in water, it can conduct electricity. However, if I just want to stick a battery into just salt itself, it cannot conduct electricity in its solid state. So Caleb now wants to try to melt salt at home. The melting point and boiling point of salt is extremely high. You can try, but I don't know how long it will take to melt it. Okay, oh, that's a good question. Most ionic compounds can dissolve in water, but you learn in JH3 onwards that some cannot. Yes?
Since if the ions are dissolved in an aqueous, like that, yeah, if it's salt, right? So the ocean is also like salt water.
Yes.
So if lightning struck the ocean, would just all the fish in the water get electrocuted?
That's a great question. So technically, if lightning strikes the ocean, does it conduct the electricity? It does not. I don't know what happens to Aquaman now.
But like, don't all the fish die? Because
That's a great question. Actually, that's a great question. I have no idea to what extent the electricity goes. I suspect that there's a limit. One bolt of lightning cannot be an endless amount of electricity also. So perhaps the fishes in the area will be struck, but I'm not too sure.
But seawater isn't just pure salt water.
Oh, definitely not. Like there's a lot of other stuff. Okay, so that's the next point number 2. They are good electrical conductors only in molten and in aqueous state because their ions are free to move. They can carry the electricity here and there. But in the solid state, they cannot carry the electricity here and there and everywhere. Okay? So that's property number 2. And I think almost time for a recess. Okay, before I end today's lesson, I have 3 more minutes on my watch. The last property of ionic compounds. Last property is that, you look in your textbook, last 2 properties. Property number 3, it is soluble in water for most ionic compounds. Caleb's question was, do all ionic compounds dissolve in water? Most. Some do not, but you learn next time which ones don't. Okay, but most of them can. Finally, ionic compounds are hard and brittle. What does hard and brittle mean? Hard means it's hard lah. No, it is hard. It's solid. Okay, that's what hard means. Why is it solid and hard? Again, because the ionic bonds are very strong. Ionic bonds are strong. That's why it's hard. And what does brittle mean?
Break easily.
Okay, so there's a slight difference. Doesn't mean if something is hard, it doesn't break easily. Okay. Oh, sorry. It doesn't mean if something is hard, it doesn't break easily. Yeah, it's not the same thing. Something can be hard, but it can break easily. Glass is hard, but if I will slam my head hard enough on the hard glass, it can also break. Okay, so hard things can also break. So the idea here is that ionic compounds are hard, and they are also brittle. Yes. Yeah, so if you smash salt hard enough, it can break into many pieces. But the many small pieces are still hard. Oh no, you cannot smash it hard enough until it becomes ions. It can only be free ions when it's in the melted or in the dissolved state. But you cannot smash so hard until you get individual ions.
So does it like dissolve faster after you smash it?
Oh, actually that's a great question. It does. Because if you smash it into small pieces, water can help to dissolve it much easily. Okay, so why are ionic compounds brittle? Because notice that this is a plus, minus, plus, minus, minus, plus, minus, plus, plus, minus, plus, minus. Okay. So imagine now, I give it one knock at the top. Okay, I slam this from the top. I go and hit this. I give it a force from the top. I knock it. If I were to knock this from the top, this is what will happen. I shift all the ions one ion down. Now it's minus, plus, minus, plus. Okay, I give it a knock, right? But notice what happens now? Now it starts to, there are repulsive forces. The negative over here and the negative over here repel, 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 repel. So what will happen? This layer will break off. So that's what it means by brittle. It is hard, overall it's very hard, but it is brittle, it can break easily. Why can it break easily? If I were to just knock the layers will slide away each other and they will start to repel each other. That's why it's brittle. Okay, so these are the properties of an ionic compound. How I could see if you understand this particular part of the chapter is, I could ask you what the properties of ionic compound. Or I could give you the properties and ask you to identify whether it's an ionic compound or covalent compound and so on and so forth. Okay? Okay, thank you. Please go for your recess. Okay, and that's all. Next lesson, I will complete covalent compound and then we will complete your RE in class also.